Now the next is the types of crystalline solid, the classification of crystalline solid. The crystalline solid, depending upon the types of the constituent particle, as I said that if I'm using a word particle, that means it represent atom, molecule or ions. So depending on which type of particle is present in a solid, that is in a crystalline solid, on that basis here the classification has been done. If the solid is made up of ions, the name of the type of it is some different types of crystalline solid. If it is an atom, then it's a different type, and if it is a molecule, then it's a different type. Because if the particles are different, then their physical and chemical property keeps on changing. The intermolecular force of attraction between the particle changes. That's why here the classification is required. In the remaining part of the chapter, we are having only about the crystalline solid, because about the amorphous solid, nothing much is there to study. That is because they do not have a definite shape. They do not have a definite arrangement of a particle. So in the remaining part of the chapter, we are going to learn only about the crystalline solid. So let's start with the first type of the crystalline solid, that is called as molecular solid. First part, molecular solid. Molecular solid, as the name says, molecular solid, that means here the constituent particles are molecule. Here the constituent particles are molecule, means they are made up of molecules. Now the molecular solid is a one where intermolecular force of attraction is considered as a very weak force of attraction, and that's why that is here the force of attraction present between the particle, that is between the molecules of a solid, is a weak force of attraction, and that's why the majority of the molecular solid at a room temperature, that is at 25 degrees Celsius temperature, are in either gaseous state or it is in a liquid state. But when the same liquid is cooled, it gets converted into solid state, and that solid comes under the molecular solid. Majority of the molecular solid, example I can say the ammonia solid, carbon dioxide solid, sulfur dioxide solid, hydrogen solid, solid chlorine, solid bromine, etc. So they all are a molecular solid, but at a room temperature they all are either in a gaseous state or they all are in a liquid state. And as I said, the reason behind the reason behind that they are existing in a gaseous or liquid state is that weak force of attraction, weak intermolecular forces, which do not hold the molecule so tightly that they remain in a solid state at a 25 degrees Celsius temperature, that is a room temperature. So let's see the different type. Again, the molecular solid. The molecular solid again classified into three more categories, depending on which type of molecules are used for making a molecular solid. Here we have the two types of molecule. The one is called as a polar molecule and the second is called as a non-polar molecule. Now, what is the difference between a polar molecule and a non-polar molecule? We had already learned many times this word, heard this word, that is a polar and non-polar. Let's see once again what is polar and non-polar. If I'm saying a non-polar molecule, example I can say chlorine molecule, Cl2. In Cl2, the two chlorine atoms are bonded by the covalent bond, and in this case both the chlorine atoms, since the atoms are same, that's why they will have a same electronegativity, and if they have a same electronegativity, then it will be considered as a non-polar molecule because the dipole moment is going to be a zero. But when I'm saying a polar molecule, the polar molecule where atoms present in a molecule carry certain partial positive and partial negative charge due to the difference in the electronegativity. For example, I can say HCl. If I'm considering HCl here, we all know that the chlorine is a highly electronegative atom. Highly electronegative means it have a more tendency to pull a shared pair of electron, and since it pulls shared pair of electron, that's why chlorine carry partial negative charge, and by default hydrogen will carry partial positive charge. And since the atoms start carrying a charges, that's why it is called as a polar molecule. A polar molecule have some specific non-zero permanent dipole moment, while a non-polar molecule have permanent zero dipole moment. Dipole moment is a physical quantity which measures the polarity in a compound. So being a non-polar, its a dipole moment is going to be zero and it will have some dipole moment. Okay, so depending on which type of molecules are there, which are present in a molecular solid. On that basis, as I said, they are again classified. So let's see the types of molecular solid now. First type of molecular solid we have non-polar molecular solid. So this is the first type which we are having, that is called as a non-polar molecular solid. As the name says, we can easily predict that here the solid is made up of non-polar molecule. So here I can say that the constituent particle, Cp, that is a constituent particles which are non-polar molecule. This is non-polar molecule, and here the intermolecular force. Intermolecular force of attraction, that is attraction present between the molecule, is London force or dispersion force, or I can say weak van der Waals force of attraction. The example for this non-polar molecular solid, I can say it is solid H2, solid Cl2, solid CO2, solid iodine, solid bromine. These all are the examples of this non-polar molecular solid. So non-polar molecular solid, as I said, the molecules are non-polar. So for example, suppose if I am considering the same chlorine solid. Now in case of chlorine solid, this is first, in case of chlorine solid, the large number of chlorine molecules will be attracted with each other by a such type of force of attraction. So this is the first molecule of chlorine and this is the another molecule of chlorine. Both are non-polar. The reason because both the chlorine atoms will have a same electronegativity. So in this case, the attraction present between them is called London force or van der Waals force of attraction, which is considered as one of the weakest force of attraction. But at the same time, I will say the van der Waals force of attraction is stronger force, becomes strong force of attraction as the size goes on increasing. Because in the case of iodine solid, which is again an example of a molecular solid, in case of iodine, the van der Waals force of attraction becomes too strong that it holds the molecules into a solid state. The reason because it becomes very strong in case of iodine, because the iodine solid is a bigger, the size of a molecule, iodine molecule is a very big. Second, here I had considered the carbon dioxide, CO2. The CO2 is made up of two different atoms. So if it is made up of two different atoms, then the question arises that how it is going to be a non-polar molecule, and that too when it is bonded with the oxygen which is considered as a second most electronegative atom. So if the carbon is bonded with the oxygen, then the question arises that the molecule should be polar. Then why we are considering as a non-polar? Let's see the reason why carbon dioxide is considered a non-polar and so why it comes under this category. Carbon dioxide, the structure of carbon dioxide, it is having a linear structure where the carbon undergoes sp hybridization, so linear structure. Now let's see the dipole moment for the carbon dioxide. The dipole moment, we all know that it is a vector quantity and we represent it by the arrow pointing toward the more electronegative atom. So in case of carbon dioxide, oxygen is a more electronegative. So being a more electronegative, the dipole moment is in this direction and here the dipole moment is in this direction. So ultimately oxygen is a highly electronegative atom. This is the dipole moment in this direction and this is the dipole moment in this direction. So net dipole moment will be equal to 0. Since, as I said, the dipole moment is a vector quantity and both the dipole moments are in an opposite direction, so they are going to nullify each other and therefore the net dipole moment will become 0. And once the net dipole moment becomes 0, the molecule will become a non-polar molecule. So one CO2, another CO2, both are non-polar. So the attraction between them is going to be a van der Waals force and hence it comes under the category that is non-polar molecular solid. Then after this, the second type of the crystalline solid. Polar molecular solid. Polar molecular solid. Now what is polar molecular solid? As the name says, here the constituent particles are going to be a polar molecule. And the intermolecular force of attraction, that is the attraction present between the molecule, is here called dipole-dipole interaction. The attraction present between two polar molecules is called dipole-dipole attraction. So in the case of this, as I said, here the molecules are polar molecule. Let's see the example for this. Here the example I can say, solid HCl at a room temperature, HCl is again in the gaseous state, and when it is cooled it get converted into solid, and the solid which we are getting from HCl is called as a molecular solid. That is, and in molecular solid it is called polar molecular solid. Solid HCl, solid SO2, solid HI. So these all are considered as a polar molecular solid. Now let us consider the example solid HCl. HCl, it is a polar molecule. This is the first HCl, and this is another HCl molecule. In a solid state, we all know that there will be some attraction, strong attraction present between them. In case of this, chlorine is highly electronegative, so will carry partial negative charge, will pull the electron toward itself. Hydrogen will carry partial positive charge, similarly here partial negative and partial positive. And so that the negative part of this molecule will start attracting the positive part of this molecule, and hence the attraction present between them, the attraction will exist between them, and that attraction is called as dipole-dipole attraction. So it is called a dipole-dipole interaction in the case of polar molecular solid. Now in this case, that is dipole-dipole interaction. Again here SO2 which looks like a carbon dioxide only, but carbon dioxide, I said, it is a non-polar molecular solid, while the SO2 is considered as a polar molecular solid. The reason for calling SO2 as a polar molecular solid is it's a structure. SO2, this is the structure of SO2. It is having a bend structure. Here let's measure the dipole moment. The dipole moment in this case will be in this direction, and here the dipole moment will be in this direction. So net dipole moment is toward the downward side. So both are like directing in the lower side, so they are not cancelling each other, and they do not cancel each other means will have some dipole moment. Means the dipole moment will not be equal to 0. If the dipole moment is not equal to 0, then in that case sulfur dioxide is going to be a polar molecule, and since it is a polar molecule, that's why it will comes under a category that is called as polar molecular solid. So this is the second type of the molecular solid. Now let's see the third type of the molecular solid. Hydrogen bonded molecular solid. Hydrogen bonded molecular solid, here the constituent particle. Hydrogen bond is not the name of any molecule, it's a type of the attraction, force of attraction. So here the constituent particle, which is again a polar molecule. And the intermolecular force of attraction is called as hydrogen bond. The example, solid HF, solid ammonia, solid H2O, that is solid H2O means I can say ice. So ice is an example of the hydrogen bonded molecular solid. Or H2O, water is also a molecule, so it comes under the same category. Here, whatever the example we had considered, in all the cases, you can see that the particles are in a are molecules. Okay. Now hydrogen bonded. Here I said that if the constituent particle is a molecule, then intermolecular forces are called dipole-dipole interaction. But in this case, I am saying that the intermolecular force of attraction is a hydrogen bond. See, hydrogen bond is nothing but the dipole-dipole attraction only. It's a dipole-dipole attraction, that is a hydrogen bond. But it is considered as a strong dipole-dipole attraction. It has some extra strength, and that's why we have given us some specific name, that is a special name called as a hydrogen bond. Now, how to know whether the given substance is a dipole, the given attraction is a dipole-dipole attraction or hydrogen bond? Then for hydrogen bond, we have a simple definition. The definition is that it is an attraction present between hydrogen atom of one molecule and highly electronegative atom Highly electronegative atoms are considered as three atoms, that is fluorine, oxygen and nitrogen, that is phone atom of other molecule. So it is an attraction present between the hydrogen atom of one molecule. It is an intermolecular force of attraction. So it is an attraction present between the two molecules. So from one molecule, the hydrogen atom, from the other molecule, the atom is highly electronegative atom, that is any element from phone, that is fluorine, oxygen and nitrogen. Fluorine is considered as a most electronegative atom in a periodic table. Then oxygen comes at a second number, and the nitrogen with the electronegativity 3, it comes at a third number. Okay, now the example, let's see water. Water is considered as a ice, that is a ice. It is considered as a hydrogen bonded solid. H2O, the another H2O molecule. Now in case of H2O, we all know that oxygen is highly electronegative. So oxygen carry partial negative. Each hydrogen will have partial positive charge. So again, there is some attraction exists between them, and that attraction is called as hydrogen bond. Let's see the definition. Attraction present between the hydrogen atom of one molecule. So the hydrogen atom of one molecule, this molecule, and highly electronegative atom of other molecule. Highly electronegative, that is fluorine, oxygen or nitrogen. So here the other atom, from other atom the oxygen is present. So attraction present between the hydrogen and the oxygen, and that's why it is called as hydrogen bond. So hydrogen bond, again I will say, it's nothing but a polar molecule carrying partial positive and partial negative charge. This is also a polar molecule carrying partial positive and partial negative charge. So the attraction between the polar molecule is a dipole-dipole attraction. But as I said that the hydrogen bond is again a type of polar dipole-dipole attraction, but of having some extra strength, that is stronger than normal dipole-dipole attraction. So here that dipole-dipole attraction is called as a hydrogen bond, and we had given a name hydrogen bond simply because the molecule or the attraction is according to the definition, that is a attraction present between the hydrogen of one molecule and highly electronegative atom of other molecule. Now in the case of this is also dipole-dipole attraction. Now question arises, can I call this attraction as a hydrogen bond? Then let's see whether the definition is applicable for this attraction or not. It is an attraction present between the hydrogen atom of one molecule and highly electronegative. Chlorine is a highly electronegative atom, but its electronegativity is not too high like the fluorine, oxygen and nitrogen. So electronegativity, since chlorine doesn't come to this category, so this attraction will not be the dipole-dipole hydrogen bond. See, this strength of a dipole-dipole attraction depends upon these opposite charges. Stronger the positive and negative charge on the atoms, stronger will be the attraction. Here if the electronegative atom is a very strong, high electronegative atom, so it will pull the electron to a high tendency or to the higher extent. so that this will carry a strong or high negative charge, and that's why the strong attraction, which is not in the case of this molecule, and that's why we just call it as a dipole-dipole attraction. So we have these three types of a molecular solid depending upon which type of molecules are present, that is a non-polar, polar and hydrogen bonded solid. Now let's again compare the three types of solid on the basis of the some characteristic or on the basis of some properties. The first property, the physical state and the or physical nature. Generally, all of them are in a liquid state or in a gaseous state. Sometime if the molecule is a very big in size, in the case of non-polar molecular solid, then like for I can say the iodine, where the molecule is a very large, so the van der Waals force of attraction is very strong, then it may move to the solid state. But majority or in general, I can say that they all are in a gaseous or liquid state. Here in case of this, from all three, I can say this here the intermolecular force of attraction is the weakest. In case of polar, compared to this, the attraction is a strong, and in case of hydrogen bonded solid, the attraction is still stronger. Again, I will say the van der Waals force of attraction is generally weaker than these two, but as the size increases, the attraction goes on increasing, and the van der Waals force may become stronger than these two also, depending upon the size, as I said in case of iodine. Okay, but in general, it is the weakest attraction. So here they are the when a non-polar molecular solid get converted into a solid state due to the weak force of attraction, I can say that they produces a soft solid. While in the case of this polar molecular solid, they also produces a soft solid on the cooling. That is when a polar molecular solid we have, that polar molecular solid is considered as a soft solid, while the hydrogen bonded molecular solid is either it may be soft or it may be hard also. Then second is about the melting point. Melting point. Intermolecular forces are weak for all three. Hydrogen bond is a strong attraction, but in case of gaseous or liquid state. But when the same attraction is compared with the attraction present in a solid state, then this attraction is a weak. So ultimately all three are having a weak force of attraction. So I can say that molecular solid have the weak low melting point, and that's the reason that they are existing either in a liquid or gaseous state. But from these three, this is having the lowest melting point than this, and from all three, this is having the slightly higher melting point. The third one is enthalpy of fusion. Enthalpy of fusion, that is the energy required to convert a solid into liquid state. And if you wanted to convert a solid into liquid, simply you have to break this intermolecular forces by supplying energy. And since here the intermolecular forces are weaker one, that's why a very small amount of energy is required to break those attractions. So I can say that molecular solid, in general, the molecular solid have the low enthalpy of fusion. A small amount of energy is required here. But from these three, again, if I am comparing, then in the case of non-polar molecular solid, this require the lowest enthalpy, means this have the lowest enthalpy of fusion. Comparatively here, more energy is required, that is enthalpy of fusion is high, and compared to these two, this have relatively higher enthalpy of fusion. Then after enthalpy of fusion, the fourth one is conductivity. Whether they are good conductor of electricity or not. I will say that molecular solids are bad conductor of electricity, whether it is a non-polar, polar or hydrogen bonded solid, because for conducting electricity either the electrons are needed or free ions are required. So here they do not have any free electrons, and suppose if I'm talking about the ions also, then they do not have free ions in a solid state. Here we are talking about a solid. Water conduct electricity. Water is a weak conductor of electricity. But water conduct electricity only in a liquid state. But when the same water get converted into ice, then ice becomes a bad conductor of electricity, because water is a conductor because water contains H plus ion and OH minus ion, which is not present in the case of this. It doesn't have H plus ion, OH minus ion. This non-polar molecular solid, this doesn't conduct electricity. So in general, the molecular solids are bad conductor of electricity as they do not contain any free electron or free ions. So This is about the molecular solid. Three types and their properties. Now let's see the second type of the crystalline solid, that is called as a ionic solid. Ionic solid, as the name says, that here these are the solid which are made up of ions. Means I can say that in this case the constituent particles are ions. Ions, so we have two types of ions, that is called cations and anions. So here both are present, that is a cations and anions. Cation, that is a positive ions carrying a positive charge, and the anions which carry negative charge. Now in case of ionic solid, let's see how the particles are arranged in case of ionic solid. How the solid appears, that is arrangement of particles. Okay, so this is the crystal lattice of an ionic solid which contains the cation as well as anions. Here you can see that no two cations or no two anions comes together. After every cation there is an anion, and after every anion there is a cation. Let's see, this is a, suppose this is a crystal lattice of a NaCl. So here I can say that these positive ions are nothing but the Na plus ion, and the negative ions are nothing but the Cl minus ion. Since they are carrying opposite charges, so they are attracting each other, and the attraction between them is called as this electrostatic, that is opposite attraction because of the opposite charge is called as ionic bond. So in case of ionic solid, the attraction or the bond which holds the ions together is called as an ionic bond, and ionic bond is considered as the one of the strong bond or strong force of attraction. And since the force of attraction is strong, so simply I can say that it will be a hard in nature, as well as the high energy will require to convert ionic solid into the liquid state. So here I can say that the bonding, that is the attraction between the ions, is ionic bond. Example I can say that all ionic salts such as NaCl, KCl, CaCl2, etc. These all are ionic solids which are considered as here ionic. These all are the ionic salts which are considered as an ionic solid. Now in case of ionic solid, let's see their characteristic. The characteristic number one, since the attraction between the ions is a very strong attraction, that's why it is considered as, that is a ionic solids are considered as a hard in nature. So they are hard and brittle. It means they are very hard, the attraction is very strong, but at the same time if you want to break, it can be broken easily. Then second one, since the attraction between the ions is a very strong attraction, due to that strong attraction they have a high melting point. And third, since the melting point is high, so simply I will say that have high enthalpy of fusion also. Enthalpy of fusion, that is the energy required to convert a solid into liquid, and which is possible after breaking this attraction. And since the attraction is strong, so more amount of energy will require to break this attraction. After this, if I am talking about the conductivity, then I can say here we have, in case of ionic solid, which is made up of ions, but still they are bad conductor of electricity. They do not conduct electricity in solid state, because in solid state these ions are bonded by a strong ionic bond, and for conduction of electricity we require free ions, that is which can move, but due to the presence of these ions, it cannot, the ions are, due to the presence of such a strong ionic bond, the ions are not free to move, and that's why the ionic solids are bad conductor of electricity. But they are bad conductor of electricity in solid state, but when they are converted into liquid state or in a molten state, the molten state or the liquid state, then it start conducting electricity, because in molten state means we are converting a solid into liquid. So when it is converted into liquid, this force of attraction breaks and the ions get free, and once ions get free, they start conducting electricity. The same thing happens when they are added in water also. When the NaCl is added into water, we all know that NaCl, the ions between the Na plus and Cl minus breaks, and we get free Na plus and Cl minus. So ionic solid do not conduct electricity in solid state. But at the same time, in molten, that is a pure liquid state, or aqueous means where the solid is dissolved in water. So it conducts electricity in a molten state or in aqueous state, but does not conduct electricity in solid state. So this is about the second solid, that is second type of a crystalline solid, that is ionic solid. Now let's talk about the third type of ionic solid. Crystalline solid, and it is known as metallic solid. Metallic solid, here in this case the constituent particles are cations placed in a sea of electron. So here the cations, here the metallic solids, the ionic solids are made up of cation as well as anions, but metallic solid made up of only one ion, that is called as it is made up of only one ion, that is called as a cation. So cations which are placed in a sea of electron, and here the intermolecular force or the bonding which is present between the ions which hold the components or the particles in a solid state is called metallic bond. In case of metallic solid, the bond is always metallic, so metallic bond. Now let's see the crystal lattice of, or the lattice of a metal. So this is a metal. These are the positive ions which are placed in a sea of electrons. This dash or dot is nothing but the electrons. So here the free cations are called as a kernel, and these electrons are called as, means this other thing is called as a sea of electron. So here the cations are positive ions are called as a kernel. For example, suppose if it is a copper solid, then these are going to be a copper ions and which are placed in between the sea of electron. Now these electrons are where these electron comes, then I will say these are nothing but the electrons which are present in the valence shell of the same metal ion. Means these are the ions, these are the electrons which are present in the copper, in the valence shell of copper, but these ions are free to move, means they can move, means these ions valence electron are not restricted to a same position, they can move here and there, and after applying energy, these ions becomes, or these electrons becomes free, and hence they start conducting electricity. So since there is a free movement of electron, and that's why we can say that metallic solids are good conductor of electricity. Covalent ionic solid and the molecular solid, they are bad conductor of electricity in a solid state, but the metallic solid is the one which conduct electricity. Now let's see the characteristics of metallic solid. The first characteristic, they are hard as well as soft. Means some metallic solids are hard while some of them are soft. Example I can say, that is generally the metals which are belonging to the transition elements, they are hard in nature, but at the same time the alkali metals or alkaline earth metals like sodium, potassium, they all are considered as a soft metal. Second, metallic bond is again considered as a strong force of attraction. So I can say that they have high enthalpy of fusion, high melting point, since more amount of energy is required to convert a solid into liquid state. Then third, they have high enthalpy of fusion. Again, high enthalpy of fusion, because the metallic bond, there is an attraction present between the particle, is a strong attraction. They are considered as a good conductor of electricity in solid state, and the reason behind it is the presence of free ions. So good conductor of electricity. They are malleable and ductile. They are malleable and ductile. That means on hammering they can be converted into a sheet or can be drawn into the wire. Now question arises that on hammering, why the size of a metal increases? See, if I'm hammering an ionic solid, that is, for example, if I'm taking a salt and when the hammering is done, or if I'm taking a ice, that is a molecular solid, and hammering is done, then on hammering generally the fractures occurs, means their solid breaks. But in case of metallic solid, when the hammering is done, instead of breaking, instead of fracture, their size goes on extending. That they increases their size. So what's the reason behind it? So now let's see what happens in case of metallic solid, that on hammering its size increases. So this is a metal. Now it has been observed that the metals are made up of a large number of layers. So they are made up of layers. So they are made up of layers. So in this case, what happens when the hammering is done? Suppose if the hammering is done on the upper part. So as the hammering is done, as some force or the stress is applied, the upper part of this metal from a particular layer, it extended. Means suppose from here, if the hammering is done, so this much area from this layer, the part will move ahead. That means it will appear like this. From here, it will move to this region. On further hammering, it will again move ahead. That means the layers will keeps on moving on each other, and that's why the size goes on increasing. But since such type of layers are not present in the case of other type of solid, so on hammering, the ionic solid or the molecular solid breaks instead of increasing its size. Okay, after that they have luster. That is a metallic solid. These are the some special properties of a metallic solid. That means they are malleable and ductile, and they have a luster. Luster, that means they shine. And the reason for shining of the metal is again the presence of free electrons. Because of the free electron, they shine. So this is about the second two more solids. That is the ionic solid and metallic solid. Ionic solid, where the particles are cation and anions, which are bonded by the ionic bond, strong force of attraction. That's why all the ionic solid at a room temperature are in a solid state. Metallic solid, the constituent particles are cations, which are placed in a sea of electron. Here the cations are also known as, that is a positive ion, as a these cations are known as a kernel. Example, I can say all the metals, copper, silver, gold, sodium, potassium, rubidium, cesium, all the metals are considered as a metallic solid. For the metallic solid, in case of metallic solid, I can say the metallic solids are made up of the layers, and due to presence of a layers, when the hammering is done, their size goes on increasing, and that's why we say is that they have a malleability property, and they have the large number of free electron, and that's why they are good conductor of electricity. Now metallic solid, generally all the metals are in a solid state at a room temperature except mercury. Mercury have a low melting point up to 234 Kelvin, which exists in a liquid state at a room temperature. Except mercury, all are in a solid state. Sometime we say that gallium also exists in a liquid state, but the gallium, its a melting point is somewhere 30 degrees Celsius. Means if the room temperature is above 30, it will be in a liquid state, but if the room temperature is below 30, then it is in a again solid state. Now let's see the fourth type of the crystalline solid, that is called as a covalent solid. The covalent solid Here the covalent solid, it is given on the name is given on the basis of the interaction or the intermolecular attraction present between the particles. Actually here the solid is made up of, that is a constituent particle is atoms, and the bonding between those atoms is nothing but the covalent. A continuous system of covalent bonding is going on between the atoms, and that's why, so here that's why the name is given, that is a covalent solid. The example for the covalent solid I can say that is a carbon, silicon carbide, silica, graphite, etc. These all are the examples where the covalent bonds are present between the atoms. Now let's see the characteristic of a covalent bond. The characteristic, a covalent bond is a covalent solid is a hard in nature. Generally they are hard in nature and having a very high melting point and high enthalpy of fusion. And generally a covalent solids are bad conductor of electricity except some exception. Now while talking about the covalent solid, let's see the different forms of a carbon. The carbon is considered as a covalent solid, and here we have some different form of a carbon. Carbon, which is a polymorphic substance, and being a polymorphic substance, the carbon exists in a 3 different crystalline form. That is, first one is called as a diamond, second is called graphite, and third is called as fullerene. So we have 3 different forms of a carbon, that is a diamond, graphite and fullerene. 3 different form means all 3 are made up of carbon atom only. They are, in all 3 the carbon atoms are bonded by the covalent bond, but the arrangement of carbon is different in case of diamond, in case of graphite, and in case of fullerene. Means in all the cases the arrangement of the particles are different, but the same arrangement, once whatever the arrangement is there, the same arrangement keeps on repeating in the given substance as it is a crystalline solid. So for the diamond, now let's see the structure of a diamond. Now in case of a diamond, here you can see that in the case of this carbon, each carbon atom is bonded with the 4 different carbon atoms, that is in a tetrahedrally manner. So in case of diamond, each carbon is tetrahedrally bonded with the 4 different carbon atoms. Means in this case I can say the carbon undergoes sp3 hybridization. Carbon whose electronic configuration is 6, that is having atomic number is 6 and having a configuration 2,4, that is a 4 electron in outermost orbit. But since in this case each carbon atom is forming a 4 covalent bond, so all 4 electrons are utilized for the formation of the bond, that is a covalent bond, and that's why the carbon do not have any free electron, and that's why the diamond is considered as a bad conductor of electricity. In this case, the carbon atoms combine together and form a network solid. A very giant structure is formed by the carbon in case of diamond. The diamond is considered as one of the hardest elements whose melting point is approximately 3550 degrees Celsius, and which is used for cutting the glasses or the metals, and is also used for making ornaments. The second polymorphic substance or the polymorphous form of the carbon is a graphite. In case of graphite, each carbon atoms combine together and form a hexagonal ring and those hexagonal rings combine together and form a layer, and many layers are there, and each layers are and between those layers certain force of attraction is present. Now when the carbon atom is forming a hexagonal ring, in that hexagonal ring each carbon atom is bonded with the 3 different carbon atoms, and here the carbon undergoes sp2 hybridization. In this case, the carbon undergoes sp2 hybridization. So when carbon combines with the 3 carbon atom, when it is combining with the 3 carbon atom, then carbon, while combining with 2 carbon atom, it is bonded by the single bond, while with the 3rd carbon atom is bonded by the double bond. Double bond means there is a sigma bond as well as pi bond in the case of graphite. And since the carbon contains the pi bond, which contains a pair of electron, and pi electrons are known as delocalized electron, and that's why, since it have a delocalized electron, that's why the graphite is considered as a conductor of electricity, means it conduct electricity. Now in case of a graphite, the layers are connected by some force of attraction. There is some force of attraction present between those layers, and that force of attraction is called as a van der Waals force of attraction, which is considered as a weak force of attraction. And due to that weak force of attraction, these layers can move here and there, and since there is a movement of layer, that's why the graphite is considered as a slippery in nature. It slip like a grease, I can say, and that's why the graphite is also used as a lubricant. The third, fullerene, third polymorphic form. In case of graphite, I said that carbon atoms undergoes sp2 hybridization and they combine together by a covalent bond and form a hexagonal ring. But in case of fullerene, the carbon atom, this is considered as the most unstable form of from three unstable form of the fullerene. Unstable form of the carbon. Fullerene, in this case, the carbon again undergoes sp2 hybridization. Here the carbon atoms combine together and by a covalent bond and form pentagonal ring as well as hexagonal ring. And these pentagonal ring and hexagonal rings combine together and they form a spherical shape. It looks like a ball. So spherical in shape, which contains a large number of pentagonal ring and hexagonal ring. Depending on the condition, the fullerene which form contain the different number of carbon atom in a sphere. Some sphere of a fullerene contains 60 carbon, some of them are containing 70, some contains 100, some contain 150. The number of carbon atoms varies, but the fullerene which is considered as the most stable is containing 60 carbon atoms in a sphere, and hence that fullerene is known as a C60. And if I am considering a C60 fullerene, then it contains 20 hexagonal ring and 12 pentagonal ring. In this fullerene also the carbon undergoes sp2 hybridization. That's why this is also having a pi bond, that is a pi electron, that is a delocalized electron. That's why fullerene also acts as a good conductor of electricity. When fullerene is treated with the potassium, it forms a compound like K3C60, which acts as a superconductor at a temperature of 18 Kelvin. Superconductor means where the resistance becomes zero at a very, very low temperature, that is 18 Kelvin. So these are the three different forms of a carbon, that is a diamond, graphite and fullerene, where in case of diamond the carbon is sp3 hybridized. This is a bad conductor of electricity. In other cases the carbon is sp2 hybridized and they are good conductor of electricity due to the presence of delocalized pi electron.